Ikehata is from National Agricultural and Food Research Organization, Tsukuba, Japan, where he is the United Leader of Non-Destructive Evaluation Unit. He has been working with various spectroscopic techniques, including NIR, UV, and IR spectroscopy, and his presentation today is about opening the black box of NIR prediction for sugar content of fluids, the complementary analysis by Aquaphotomics and metabolomics. The floor is yours.
Thank you very much for our kind introduction, Zoltan-san, and thank you very much for giving me a great opportunity to talk about my ideas today. Okay. My name is Akifumi Ikehata, but call me Aki. Maybe this is good to remember. Aki is my name. Okay, before my talk, I want to briefly introduce my institute. My institute name is National Agriculture and Food Research Organization. The name is so long, so normally the people use the abbreviation NAR or NARO. Okay, call it NARO. NARO is the core institute in Japan for conducting research and development on agriculture and food. NARO is the one of the giant institutes in Japan. The institute is giant, but my group is consists of a small number of members. The name of my laboratory is Non-Destructive Evaluation Unit. In Japanese, HIHA. And but this laboratory is very important because this is the first laboratory for NIR application in Japan. So 32 years old this year. And the mission of our Non-Destructive Evaluation Unit is to establish the principle and applications of non-destructive analysis methods using light. So now our group used various kind of spectroscopic technique, IR, Raman fluorescence, far ultraviolet, and of course UVBs and NIR. But we are still strongly promoting near-infrared spectroscopy. This is not because of the historical reason, because NIR is really powerful for prediction of components in food and agriculture products. So for example, as Professor Tenkova explained yesterday, non-destructive measurement of sugar content of the fruits is very well-known, widely spread application of NIR spectroscopy. So if you go to the supermarket in Japan, you can find the sign indicating NIR guaranteed sweetness of fruits like that. Not only bricks, NIR can measure really various kinds of items, simple ingredients and convoluted index and physical properties as well. So important thing is how can we predict these items? As you all know, it's not difficult to get the prediction model. If you have the data set that the bricks objective variable and the explanatory variable, for example, bricks and NIR spectral combination, and if you put these data set into software, maybe you will use PLS regression algorithm, and finally you can immediately get the regression coefficients beta like this. Once you have these regression coefficients, you can calculate the predicted value of bricks, for example, like this way. Okay. However, the mechanism of the prediction model is not necessarily understood. So this is, I think, the black box. So because of the deficient band assignment. So even in the prediction of sugar content in fruits, the informative wavelength have given empirically given. So, in other words, nobody knows why we can grade the sugar contents in fruits by using the NIR spectroscopy. So, to reveal the molecule contributing the NIR prediction model, I decided to work with a specialist of metabolomics. Okay. Before we go into the experiment, I will briefly mention about the metabolomics. Metabolomics is one of the omics positioned in the downstream of the central dogma, like this. And metabolomics is an authorized comprehensive study of metabolites. What is metabolites? This is sometimes called a metabolome. This is small organic molecules who plays any role in the metabolic reactions. So to detect the metabolites, almost researchers use chromatography mass spectrometry, and the other some researchers use the NMR, nuclear magnetic resonance spectroscopy. But unfortunately, these techniques are non-destructive way, not non-destructive. Okay, now let's summarize what we observed in the NIR spectrum. We can observe the signal of metabolites themselves, okay? But we often observe the absorption band which are not assigned to any metabolites. This fact implies the necessity of a complementary analysis by metabolomics and effective water, okay? That is aquaphotomics. Okay, let's move on to the experimental. As I mentioned, NIR measurement both metabolite and water. What we observe is always ill-assigned broad overlapped peaks like this way. So we also use the proton NMR spectrum like this. So NMR is destructive, we need a juice to measurement. But this give us well-assigned sharp peaks like this. These all peaks are assigned. So this is very helpful to understand the contribution of metabolites in the NIR prediction model. We compared these two spectra and by using the statistical heterospectroscopy. I will mention in detail later. And of course, we also measure bricks. In other words, solid solvent contents. But as objective variables, this needs a juice. We have to break the sample and squeeze. So this is why we have to do the NIR spectroscopy. Okay, this slide shows the detail for the measurements. We use the sample 150 apples and 40 peaches. This is the Briggs distribution of apples like this. And the non-destructive operation, we use the visible NIR spectrum. This is portable type spectrometer provided by Kubota company. This is equipped with our interactance probe and our silicon sensor. So this covers the visible range to NIR range, short wavelength NIR range. And the destructive operation is Briggs measurement and NIR measurement. And for data analysis, I use the R. Okay, what you see here is visible NIR spectra by using the portable spectrometer, the apple spectra. Okay, as you can see here, there's a strong peak due to chlorophyll. at around 670, like this. This is colored, transmitted color is red, but looks green because it's chlorophyll. And also we can observe the very broad peak, maybe due to water in NIR region like this. So many people use the second derivative spectra to remove the baseline shift. So we just followed this operation. We created the second derivative spectra and input. This will be the input data for the analysis. Okay, before to do that, I created a PRS regression model by using the NIR spectra to predict the Briggs value of the fruit. This is a non-destructive way, so many people doing this like this, and we can get the good result by using the 1, 2, 3, 4 latent variables, and this is the regression vector, and this is selectivity ratio and the VIP. Okay, I will mention the again the regression vector again later. Okay, next slide show the proton NMR spectra of fruit juice diluted by the deuterium exchanged phosphate buffer, and here low NMR spectra is too fine to calculate the intensity. So the old NMR spectra was binned with a size of 0.02 ppm bucket. This is called a bucket integration. And also the intensity was corrected with the internal reference compound called DSS. Okay, next, just in case, I tried to make a prediction model for Briggs by using NMR spectrum. This is destructive, so nobody do this operation, I think. So, but anyway, we can get a good prediction model from destructive NMR measurement like this, and this is the regression vector and the selectivity ratio. Okay, and the next slide, I will explain in detail about this regression vector. Okay, this slide shows the regression vector for the prediction of Briggs and this black. And these colors are spectra of model solutions of different type of sugars and malic acid. These are major components of apples. So as you see here, regression coefficient, shape of the regression coefficient is very similar to the apple juice sample this way. And also these peaks can be assigned by the model solutions like this. For example, this is due to a sucrose, this is due to a glucose, like this way. Okay, so as you see here, proton NMR spectra is very well assigned. So now let's compare NMR and NIR spectra by a statistical heterospectroscopy. Okay, what is the statistical heterospectroscopy, SHY? This is a very simple idea. This technique was introduced by Nicholson's group. This is a very famous group for NMR metabolomics. And this is very simple. If we want to compare the intensity in this wavelength and in this chemical shift, you can create this kind of correlation map like this for the, for example, in apple 150 plots like this, and you can calculate the correlation coefficient like this. So if you get the positive good correlation, this calculator put the dot in red, like this way here. if you get the negative correlation like this, the software will make a dot like this. Okay, this is how to get the SHY heat map. Very easy way. Okay, what you see here is the result of the heat map of apple. Okay, we can observe the high positive and the negative correlation along with the vertical lines. Here 888 and here 904 nanometer. We also observe the small positive spots around the 790 and 830. All these spots appear on the NMR bands of sugar. Here. These you can see are strong peaks due to sugars. Okay. So let's check the prediction model of the bricks again. So we will make our projection in this direction in next slide. This figure shows the mean correlation coefficient of the heat map at each wavelength. So as you see here, this 888 and the 904 is important for prediction, but also 800 and the 28 is or this is also important for the prediction, right? And we can compare this result to the prediction model by using the PLS model. This shape similar to the regression vector of the NIR prediction model like this. And also selectivity ratio tells us the importance of this wavelength and this wavelength, 888 and 904. This is very surprising result. Okay, next, take a look at the cross section of this dotted line in the next slide. Okay, this is cross section. That means the correlation coefficient at the marker wavelengths. Marker is this wavelength and this wavelength. As you see here, the shape of the curve is very symmetric. So, and these peaks can be assigned by the comparing the spectra of model solutions of sugars like this, and I indicated all peaks colored. So here I can say in case of apple, this is the summary, a brief summary of apple. These two maybe I think this is like a movement of seesaw. So this kind of movement can be frequently observed in the water band of NIR spectra. So I think that these are due to water perturbated by sugars. Sugars are these are sorbitol, fructose, glucose, and sucrose. This is a very major glycometabolism in the fruits. Okay, this is the mechanism of the prediction model of apple. Okay, next I will show you the case of peach. That's so different. You can see the vertical line here. This is 830. This can be observed also in apple, but dominant one is this horizontal lines. What is that? The answer can be seen here because we have put the assignment here along with the NMR spectra like this. So for example, in this case, this is due to galactonic acid. And this is, I don't know, at this moment. This is also no idea. But this is, here's the answer. This is methanol. method. What's that? So I checked, I searched these metabolites in the database of the metabolic pathway. I found the reactions like this. This is a major reaction in peach. This is a hydrolysis of pectin. Pectin is a polymer of sugar chain. So this can hold the firmness of the peach. But you know, peach is easily to become, you know, softer and softer.
Right.
Yeah, that is ripening. So in the ripening, during the ripening, pectin will decompose into the pectate, and the decomposed product is galacturic acid. And also, in this reaction, the water and the methanol was used. So we can say, in the case of peach, the dominant factor are not only the sugars, but also ripening. Okay, finally, let's summarize my talk. What I told today is very special for living system, not for artificial product. This is premise, okay? And metabolic pathway is now well known, and you can check it in a web database, for example, KEGG in Kyoto University, something like that. However, there's no way to study metabolic reaction in real time. Okay. So now, as you understand, we are just now standing on the start line, but our final goal is to upgrade the NIR to real-time monitoring tool for rigging system. Okay. So, but because NIR is, I think, this is my opinion, NIR is unique method for this purpose. Okay, but we need advanced analysis methods combined with, for example, a kind of system biology or something to solve this problem. So if you have a good idea, don't hesitate to come to us, and I welcome your opinions. Thank you very much. That's all.
We run out of time. Anyone, one short question? Then I have one, just to have one question about the bricks. As far as I know, the bricks distribution inside an apple is very inhomogeneous. How did you measure the bricks?
Yeah, I just measured the measuring side of the NIR spectroscopy. So, yeah, I just measured only one part. Maybe it's in the equator of the food.
Thank you very much. Let's thank him again.